Welcome to the deep dive. Today we're tackling, well, a really fascinating area of AI, how computers are learning to describe specific details within images and videos.
hmm
We're talking about detailed localized captioning. So not just, identifying a car in a picture.
Right, but getting down to the nitty-gritty, like the style of its headlights or maybe the texture of the tires,
Yeah,
specifics.
exactly. And this feels crucial, right? Moving beyond just basic recognition towards like actual visual and understanding.
It absolutely is. If an AI is going to interact effectively with the world, it really needs to discern and articulate granular details and, importantly, their context.
Which brings us neatly to our focus for this deep dive, a new model called DAM, that's D-A-M for Describe Anything model.
hmm
Our main source here is the research paper Describe Anything, Detailed Localized Image and Video Captioning. We're going to unpack what makes DAM a potentially significant step forward.
Yeah, and what's really interesting, I think, is how DAM tackles some core limitations of earlier methods.
Like what?
Well, the researchers point out that previous approaches often suffered from a kind of loss of regional details early on in the image processing pipeline.
Okay,
Think about trying to describe, say, a tiny inscription on a monument. If the system sort of blurs those fine details right at the start.
you've lost it. You're never getting an accurate caption for that specific bit.
Precisely. It's like trying to read fine print on a really bad photocopy. The clarity is just gone.
Right. The paper also mentions degraded understanding when the regional context is missing. Why is focusing too narrowly a problem?
Well, you see, if you only show the AI a tiny isolated pack of pixels, it lacks the broader scene to really figure out what it's looking at.
Oh, okay.
A close-up of, I don't know, a metal ring, could be jewelry, could be part of a machine, could be loads of things.
Right.
It's the surrounding visual information, the context, that gives the necessary clues for accurate identification and description. And DAM's innovations are really geared towards tackling these two issues together, detail and context.
Okay, let's dive into DAM's architecture then. The paper mentions two key parts, the focal prompt and the localized vision backbone. What's the main idea here?
So the focal prompt is, well, a pretty clever way DAM feeds the model both the detailed info about the specific area and the wider context.
How does it do that?
It combines the complete image with a zoomed-in crop. They call it focal crop, centered right on the region we want described.
Okay, the target region.
Exactly. And crucially, both the full image and that focal crop come with masks. These masks precisely outline the regional interest.
So it's like showing the AI the whole puzzle board, then saying, okay, now let's really look closely at this specific piece. And the masks point exactly to that piece.
That's a great analogy. And the paper mentions expanding the bounding box of this mask, by a factor alpha, often around 3.
Right, why expand it? Why not just the exact pixels of the object?
That expansion is really important for grabbing the immediate visual neighborhood of the region.
Okay.
If you only focus on the object's pixels, you might miss key relational cues. So by slightly expanding that boundary, though, they set a minimum size to like 48 pixels so it doesn't get ridiculously small. DAM ensures the model gets enough local context.
That makes sense. Describing a door handle needs a bit of the door, right?
Exactly. You need to see its placement.
So how does DAM actually handle these masks, the localization inputs themselves?
Well, interestingly, they treat the masks quite similarly to how vision transformers, VTs, process image patches.
Okay, like breaking the image down.
Yeah, just like an image gets divided into patches and turned into numerical embeddings, the masks are sort of embedded and integrated with their corresponding full image representation using another embedding layer. It lets the model directly process that spatial-aware information.
Got it. So the model gets the visual data, image, and crop, and the spatial data, the mask. Now, about the vision encoders, there's a global one, FG$, and a regional one, FR$. What do they each do?
Right. The global vision encoder, FG$, looks at the full image and its mask. Its job is to extract the overall, global visual features. Let's call them Z$.
Okay, the big picture features.
Think of it as the contextual awareness part. It gives the model a high-level grasp of the whole scene and where our specific region fits in.
And then the regional encoder, FR$.
That one focuses on the focal crop and its mask, and this is a really key innovation. It also takes those global features, other dollars, as input, as context.
Ah, so it uses the big picture on understanding while zooming in.
Precisely. It allows the detailed processing of the local region to be by the broader scene understanding. The output is what they call fused visual features, $, which are rich in detail about the specific region, but also context aware.
So it's tiered, grasp the scene, then zoom in, but keep the scene awareness. Okay. Now, the paper talks about gated cross-attention adapters inside FR$'s transformer blocks. Sounds complex. What's the gist?
It does sound a bit technical, but the core idea is actually quite elegant. It's how DAM blends that global context into the local feature processing.
Okay.
Inside each transformer block of this regional encoder, these adapters let the local features from the focal crop selectively attend to or focus on the global features.
Like pick out the relevant bits of global information.
Exactly that. The cross-attention finds the most useful parts of the global context for understanding the local region. And the gated part uses these learnable scaling parameters, gamma and beta, which start at 0.
Why start at 0?
That's a clever trick. It means initially these adapters have no effect, preserving the original capabilities of the pre-trained regional encoder. It allows for smoother, more efficient fine-tuning later on because you're not drastically changing things from the start.
So it's a gentle integration of global context, not overwhelming the local analysis.
Nice.
And after all that visual processing, the fused features go to a large language model, an LLM.
Correct. Along with some text prompt tokens, $2, the LLM takes the enriched visual features, the dollars, and the prompt, and then generates the final detailed description for that specific region.
And the paper really stresses that this design doesn't increase the sequence length of the vision tokens. That's good for efficiency, right?
Absolutely. Keeping that sequence length constant avoids the computational cost blowup you sometimes see. Plus, that zero initialization strategy for the new parts means they can leverage pre-trained vision language models really effectively.
So less training data needed.
Relatively speaking, yes. They mention fine-tuning with around 1.5 million samples, which is quite efficient for this kind of adaptation, thanks to preserving that pre-trained knowledge.
Okay, architecture covered. Let's shift to training. The paper calls it DLC-SDP, detailed localized captioning with self-distillation and prompting. 2 stages. Stage 1 is self-distillation.
Right. In this first stage, they use a powerful, pre-existing vision language model, basically, a high-quality, large multimodal model as a teacher.
A teacher model.
Yeah, this teacher model automatically generates really good descriptions for mask regions in images. But here's the key bit, the innovation. DAM, the student, learns to predict these descriptions without getting any initial keywords or labels for that region.
Hold on, so the teacher generates the answers, but the student, DAM, has to figure it out from scratch without any hints during training or later use. That seems different.
It's definitely a departure. This self-distillation is a smart way to generate lots of high-quality training data without needing tons of expensive manual annotation.
Okay, that makes sense from a practical standpoint.
And importantly, the paper argues this gives better quality data compared to just directly prompting a VLM to generate descriptions for distillation.
Why better? What's the edge?
It comes down to inference time. When you actually use DAM, you're not going to give it class labels or keywords.
Right.
Many existing VLMs actually perform quite poorly without those kinds of prompts. By training DAM without prompts during distillation, they're essentially forcing it to learn a more robust, more context-aware way of generating captions directly from the visual input and the mask. It has to rely purely on the visual information.
Got it. Training it for the real-world scenario from the start, like teaching essay writing, not fill in the blanks. What about stage 2 then? SSL with unlabeled data.
So even with good distilled data, you hit limits on scale. Stage 2 brings in self-training-based semi-supervised learning, or SSL. This lets them use massive amounts of unlabeled visual data.
How does that work? Learning from images with no descriptions at all?
Essentially, the model makes predictions on this unlabeled data and then uses its own, hopefully fairly accurate predictions as a kind of pseudo-label to further train itself.
Ah, bootstrapping its own learning.
Exactly. It's a form of self-reinforcement, letting the model refine its understanding using a much, much bigger data set than you could ever manually annotate or even distill. It helps tackle that data scarcity problem.
Okay, smart architecture, smart training. How do you actually measure if it's working well? They introduced a new benchmark, right? DLC bench.
Yes, DLC bench. They designed it specifically because traditional metrics, the ones relying on comparing a generated caption to just one or maybe a few ground truth reference captions, can be pretty limited for this specific task.
Limited how? What's the problem with reference caption here?
Well, the paper gives examples. Imagine DAM generates a caption that includes a perfectly correct detail about the region, something genuinely visible.
Okay.
But if that detail just happened to be missing from the reference caption someone wrote for the dataset.
Ah, the standard metrics would penalize it. Call it a hallucination even though it's right.
Exactly. It underestimates the model's true ability to see and describe detail just because the human annotation wasn't exhaustive. Which, let's face it, it rarely can be for every single detail.
That's a critical flaw if you want to measure detailed captioning. So how does DLC bench get around this?
It's a two-step process. First, obviously, DAM generates its description for a mask region in the benchmark. Second, and this is the clever part, they use another powerful LLM as a judge.
An LLM judge?
Yeah. This judge doesn't just compare strings. It answers a set of predefined positive and negative questions about the details in that specific region based on the caption DAM generated.
Okay, positive and negative questions. What's the difference?
Positive questions ask about things that should be there, attributes, parts of objects. So if the region is a bike wheel with a valve stem, a positive question might be, is the valve stem visible? Or where is the valve stem?
And you get points for getting that right in the caption.
You get a point if the caption correctly includes it, nothing if it's omitted, a penalty if the caption makes a factual error about it, and importantly, you only get positive points if the main object itself was recognized correctly.
Okay, rewards accuracy on expected details. What about negative questions?
Negative questions probe for details that shouldn't be there, like attributes of similar but absent objects or just irrelevant stuff.
Like asking if the road bike tire's knobby.
Exactly. If the caption correctly omits that wrong detail, it gets a point. If it includes the wrong detail, it gets penalized. Again, messing up the basic object recognition can lead to 0 or negative scores here too.
So it's testing both accuracy saying what is there and faithfulness not saying what isn't there. That sounds much more robust for judging detailed descriptions and hallucination.
It aims to be, yes. It provides a more nuanced picture.
How do they combine these scores?
The scores from the LLM judge for positive and negative questions are calculated, normalized to a percentage for each category, and then the final DLC bench score is simply the average of the positive and negative scores. Gives a balanced view.
Do they give an example of paper?
Yeah, they use an example of a stove with coil burners. A positive question was about where the control panel was. A negative one asked if it was an induction stove, which it wasn't. The LLM judge reads DAM's caption and answers those.
Okay, cool. So the crucial part, how did DAM actually do on these benchmarks?
The results look pretty strong, actually. On Flickr 30K entities, which is a standard phrase-level grounding dataset, they evaluated DAM 8B zero shot.
Meaning without specific training on that data set.
Correct. And it showed a 12.3% average relative improvement across metrics like blue, meter, sitter, spice compared to the previous best model. That's quite a jump.
That is significant. And what about video? It's meant for video too, right?
Yes. On the HC-STVG benchmark, which is specifically for detailed localized video captioning, the improvement was even bigger, nearly 20% relative improvement over the previous state-of-the-art.
Wow.
That includes beating Concurrent One, another model called Video Reefer. And interestingly, when they tested DAM on Video Reefer's own benchmark, Video Reefer Bench, DAM came out on top there too, both zero shot and when trained specifically on that domain.
So consistently strong performance across different benchmarks and modalities. The paper also showed some specific examples, didn't it, to illustrate its strengths?
It did. Some nice qualitative examples, like it could describe a sofa cushion accurately without getting distracted by a dog that was visible elsewhere in the frame but outside the cushion's mask.
Good focus.
Or identifying a roller blind correctly, which often needs context from the window frame.
Oh.
And describing a giraffe without mentioning birds perched on it if the mask was just on the giraffe. It shows good localization and contextual filtering.
It seems to have a good grasp of boundaries and relevance. What about that surprising capability, the zero-shot regional question answering? It wasn't trained for QA, was it?
No, not explicitly, but it showed this emergent ability. Given an image region, it could answer questions like, what color is the shirt? Or what material is the stick made of? Or what's the texture of the fish? Even recognize a strawberry in a defined box.
That's fascinating. It suggests it's learning a deeper representation of the visual content within regions, beyond just generating descriptive text.
It seems that way. It points towards a more generalized visual understanding at the regional level.
What about tricky situations, like objects being partly hidden or moving?
It showed some robustness there too. It could still describe objects reasonably well, even when they were significantly muted in parts of a video,
Okay.
and handle partial occlusion due to things like human arm movements. Plus, it demonstrated an ability for detailed motion analysis picking up on even slight movements in video clips.
And multi-view. Could it combine info from different angles?
Yes, they showed an example using the Co3DV2 dataset. It could integrate information across multiple viewpoints to generate a more complete description of an object than you'd get from just one angle.
The paper also drew a contrast with trying to use existing VLMs just by telling them where to look using text prompts. Why is DAM's approach better?
The argument is that instructing a general VLM with text like describe the object in the top left corner can be kind of clunky and less precise.
Right.
DAM's separate explicit MAM input provides a much cleaner, more direct way to specify the region, leading to better localization and potentially more accurate descriptions for that specific area. The dedicated input matters.
More like using a precision tool. Of course, it's not perfect, right? They mention limitations.
Oh, absolutely. They're upfront about that. DAM can still make mistakes in recognition. The example they gave was mistaking a frog-shaped slipper for an actual frog.
Ah, so the detailed description part might be strong, but if the initial object recognition is wrong, the description will be too.
Exactly. There's still room for improvement, particularly in that initial recognition stage for ambiguous or unusual objects.
Okay, so wrapping up, what would you say are the biggest takeaways, the main innovations DAM brings?
I think there are three key things. First, that focal prompt mechanism, the way it combines the full image, the focal crop, and the masks to feed both context and detail effectively.
Uh,
The second, the two-stage DLC-SDP training, using self-distillation from a strong teacher without labels and then scaling up with semi-supervised learning on unlabeled data. That's a significant methodological advance.
right.
And third, well, the results. The strong performance lift on challenging benchmarks for both image and video captioning really validates the approach.
And together, these tackle those core problems. We started with losing detail and lacking context, leading to, hopefully, much more accurate and useful descriptions of specific visual regions.
Precisely. It feels like a solid step towards AI systems that can understand the visual world in much finer detail.
It really does get you thinking about the potential applications. Where could this kind of detailed, localized understanding make a real difference?
Oh, the possibilities are huge. Think about robotics needing to identify and describe specific parts of objects for manipulation.
Yeah, grabbing the handle, not the blade.
Exactly. Or autonomous driving getting a much richer understanding of complex scenes, identifying specific hazards or signs more reliably. Video surveillance, too, being able to automatically generate detailed reports about specific events or objects.
And accessibility.
Absolutely. Imagine enhanced tools for visually impaired users providing really detailed audio descriptions of specific parts of an image or a scene they point to. It could be incredibly empowering.
It's quite compelling, the idea of AI being able to precisely describe any region you point to. It could genuinely reshape some of these fields.
It really could.
Well, for those of you listening who want to dig even deeper into the technical specifics, we definitely recommend checking out the original research paper. It's packed with detail on the architecture, training, and those evaluation results. Thanks for joining us for this deep dive.
Yeah, and maybe next time you look at a picture, you'll think a bit more about describing not just the whole thing, but all the little details within it.